These are the answers to homework 4C. Here are some of the definitions I would like you to know. And here are the remainder. Now on to the questions. Number 1, draw the expected d orbital splitting for a palladium positive 2 ion assuming the following geometries, showing the correct number of d electrons, and predict which geometry would be the most stable. For a palladium positive 2 ion, the palladium atom has an electron configuration of krypton in brackets 5s2 48. If it's a positive 2 ion, it will lose its 2 highest energy level electrons, which are the 5s's. So the palladium positive 2 ion will have a configuration of 48, which means 8 d electrons. For the different possible geometries, first would be octahedral. So if the palladium atom is surrounded by an octahedral crystal field, the d orbitals, which are normally degenerate, will be split into a set of 3 orbitals of low energy and 2 orbitals of high energy. The 8 electrons will be spread out, 6 in the bottom 3 orbitals, 2 in the top. And this will be the arrangement if you have an octahedral crystal field. If you have a tetrahedral crystal field, then a tetrahedral arrangement of ligands will cause the d orbitals to split in energy, but this time it'll cause 2 orbitals to be low in energy and 3 orbitals to be high in energy. The splitting energy difference between the two is going to be 4/9 the splitting energy of an octahedral crystal field, so that's why I've drawn them closer together. And the 8 electrons would spread themselves out into the 5 orbitals in this fashion as shown. For a square planar geometry, and this is where you have 4 ligands arranging around the metal in a square planar array, the energy of the d orbitals gets split such that the dx squared minus y squared is very high, very unstable. Then going down from there, dxy, dz squared, and then the dxz and yz are the lowest. Because of that large gap in energy, electrons will not fill all the way up to that orbital. So for 8 electrons, the bottom 4 orbitals will actually be filled with 4 pairs. In a linear geometry where only 2 ligands approach the metal and forms a linear crystal field, the d orbital splitting energy is the dz squared being the most unstable. Next, the dxz and yz equal, and then finally the dxy and dx squared minus y squared equal as well. The 8 electrons would once again fill the lowest orbitals in this splitting pattern. For 8 electrons, the most likely configuration for a complex with a palladium positive 2 ion with 8 d electrons would be whichever one of these patterns allows the 8 electrons to be lowest in energy as a total. And that would actually be the square planar geometry, where the 8 electrons are actually in 4 orbitals whose average energy is lower than any of the other configurations. And that's why square planar geometry is so common anytime you have an atom with a d sublevel arrangement of 8 electrons. Number 2, both NiCl4 2- and NiCN taken 4 times 2- have 4 ligands. The first complex sign is paramagnetic, the second is diamagnetic. Identify them as either square planar or tetrahedral. So in question number 2, we're going to try to take the correct number of valence d electrons for the nickel ions in both complexes. We'll arrange them in both a square planar crystal field and then a tetrahedral crystal field, and we'll see if there's a difference in terms of paramagnetic or diamagnetic. A nickel atom has an electron configuration of argon in brackets 4s2 3d8. The positive 2 ion, because it would have to be positive 2 in both of those. In each case, the complex's charge is -2, and there are 4 -1 ligands in each. So in order to make that add up, the nickels would have to be positive 2 in both. You would lose the 2 4s electrons, and the nickel ion would have a d8 configuration. So if you have a square planar geometry, the 8 electrons will fill 4 orbitals, leaving the very unstable dx squared minus y squared empty. If you have a tetrahedral geometry, the electrons will spread themselves out over the 5 orbitals like this. In this case, there is a difference in the magnetism. What we have on the left is a diamagnetic substance. What we have on the right is a paramagnetic substance due to its unpaired electrons. So if they told us that the NiCl4 is paramagnetic, that must be the second one here. And if they told us the NiCN taken 4 times 2- is diamagnetic, that must be the one that arranges in a square planar geometry. So the complex sign with chloride would be tetrahedral, the complex ion with cyanide would be square planar. Number 3, draw the d orbital splitting diagrams for the octahedral complex ions of each of the following, showing the correct number of d electrons, and identify each as paramagnetic or diamagnetic. 3a is the chromium positive 3 ion, so how would its d orbitals be arranged and its electrons if it's an octahedral crystal field? The chromium atom has an electron configuration of, theoretically, argon in brackets 4s2 3d4, but the chromium column on the periodic table is actually an exception to the electron filling pattern. One of the 4s electrons actually gets moved into the 3d sublevel to create 2 half-filled sublevels. So it's actually ground state configuration is 4s1 3d5. That actually doesn't matter in determining the configuration of a chromium positive 3 ion. You're going to lose the 1 4s electron and 2 of the 3d electrons. So whether you did that or not, you would still determine the chromium positive 3 ion would have 3 d electrons. So if you have an octahedral splitting pattern, then 3 low energy orbitals, 2 high energy orbitals, the 3 electrons to minimize repulsion would go unpaired into the 3 lower orbitals, and this would be the arrangement of the electrons in this octahedral field. And because these electrons are unpaired, this would be a paramagnetic substance. For B, for a cobalt positive 3 ion, and they said high and low spin because with the number of d electrons we're going to have here for cobalt positive 3, there's actually 2 ways the electrons can be arranged. In A, for chromium, if you only have 3 electrons, this is only the arrangement the 3 electrons can be, and there's no other choice. But for chromium, it's different. The atom has an electron configuration of argon in brackets 4s2 3d7. If it's a positive 3 ion, it loses its 4s electrons and one of its 3d electrons, so therefore it has 6 d electrons. So in an octahedral splitting pattern, there is actually 2 different ways you can arrange the 6 electrons, and it depends upon whether you assume the splitting energy is very large or very small. If it's a small splitting energy, then the electrons will spread out over all 5 orbitals, 1, 1, 1, 1, 1, and then the 6th one would finally pair up. However, if this particular complex happens to have a large splitting energy, then you have to mine the gap. The electrons will not want to promote themselves up into the high energy orbitals, and so all the electrons will stay in the low orbitals until they're filled, and only after that would they go up into the higher 2 d orbitals. So this would be the configuration if the splitting energy was really large. So in this case, the first one, which would be a paramagnetic arrangement because there are 4 unpaired electrons, and anytime you have unpaired electrons, that would be paramagnetic. This would be considered high spin because a high number of unpaired electrons. And on the right is the low spin complex with no unpaired electrons, then that would produce a diamagnetic complex. C, iron positive 3, and once again it says high and low spin, so that means there must be 2 different ways the d electrons can be arranged. Iron atom has an electron configuration of argon in brackets 4s2 3d6. To make a positive 3 ion, you would pull out the 4s electrons first and then one of the 3d electrons. So the iron ion would have a configuration that has 5 d electrons. If again we assume a small splitting energy, then the 5 electrons will remain unpaired as long as possible, occupying all 5 of the orbitals. If we assume a high splitting energy, then the electrons will only fill the lower orbitals first, and the 5 electrons would be arranged like this. In this case, they're both paramagnetic because they both have unpaired electrons, but the first arrangement we would say is a high spin because it has the highest number of unpaired electrons, and the second one, which happens to also be paramagnetic, would be considered low spin because it has a lower number of unpaired electrons. D is a zinc positive 2 ion. The zinc atom's configuration is argon in brackets 4s2 3d10. To make a positive 2 ion, you would remove the 4s electrons, so the zinc ion would wind up having 10 d electrons. And with 10 d electrons, it doesn't matter if the splitting energy is large or small. The only arrangement that those electrons can have is filling all 5 of the different d orbitals. There are no unpaired electrons. This would therefore be diamagnetic. Question number 4, identify each ligand as either strong field or weak field. In A, you have the oxide ion. The oxide ion's dot notation would look like this, and what you have in the outer shell of the oxide ion are numbers of lone pairs. If a ligand has lone pairs in its outer shell, those lone pairs will repel against the dxy, dxz, and dyz orbitals on the central metal. Those are the three lower orbitals in the energy diagram. That repulsion will cause those orbital energies to increase as they become more unstable due to the repulsion. You'll wind up getting a small splitting energy. Therefore, this is a weak field ligand because it causes a small or weak separation of the two levels of d orbitals. For B, the carbon monoxide molecule, the Lewis structure for this shows that there's a triple bond. Anytime you have double or triple bonds in a ligand, those second and third bonds of the double and triple bonds are pi bonds. They're created by having electrons in pi bonding orbitals. But if you have pi bonding orbitals in a molecule, you also have pi anti-bonding orbitals, and they're empty. What those empty orbitals do is they can attract the electrons that are in the dxy, dxz, and dyz. That causes those electrons now to attract to multiple nuclei, which means more attraction, and so their energies go down, causing a larger split in the energy, and so we call this a strong field ligand. Number 5, answer the following concerning the complex ions hexacyanocobaltate 3 and hexachlorocobaltate 3. A says give the formula for each complex ion. First one should be CO, Cn taken 6 times 3 minus. Second one should be CO, Cl6, 3 minus. B, give the electron configuration of the cobalt ion in each. It's going to be ideal. First, a cobalt atom, ask for this. Think about it. From the periodic table, brackets 4s2, 3d. And because both of these have a cobalt positive 3 ion in them, because their name says cobalt 3, you remove 3 electrons, leaving 6 electrons in the d sublevel. C, identify each ligand as strong field or weak field. A cyanide ion has a triple bond in it, which means it will have pi bonding orbitals and empty pi anti-bonding orbitals, which will stabilize the dxy, dxz, dyz, lowering them in energy and causing a big split in the two levels of the d orbitals, so that would be a strong field ligand. The chloride ion has lone pairs. Those electrons will repel against electrons in the dxy, dxz, dyz, raising their energies, making a smaller gap in energy between them and the higher two d orbitals, so therefore this is a weak field ligand. D, draw the d orbital splitting pattern for each. In this case, when you have a strong field ligand, you're going to have a big splitting energy, and when you place the 6 electrons in, they're going to fill the bottom 3 orbitals completely before they would go to the top 2, so therefore the 6 electrons would be arranged as 3 pairs. If you have a weak field ligand, there'll be a small gap in energy. The electrons will spread out over all 5 orbitals. Once the electrons have been 1 in each of the 5 orbitals, the last one pairs up, and the electron arrangement will look like this. E says identify each as para or diamagnetic. The first one has no unpaired electrons, so that means it's diamagnetic. The second one has 4 unpaired electrons, that means it'll be paramagnetic. F, identify the complex that produces a red solution and the complex that produces a blue solution. So if they're going to be colored, that means they're going to absorb some wavelengths out of the visible spectrum. So if we look at the visible spectrum, if we have a red solution, it will be absorbing a color that's the complement of red. So what's the complement of red? It's the color across on the color wheel. That would be green. If you have a blue solution, it's going to absorb its complementary color. And what's the complement of blue? It's what's opposite on the color wheel. That would be orange. So one of these solutions absorbs green light, the other absorbs orange light. So how do we relate that to the splitting energy? Well, wavelength is inversely related to frequency, and frequency is directly related to the energy of the photons. So if you are absorbing green light, those are light waves that have wavelengths that are small. If you notice, they're between 480 and 560, compared to orange anyway, which is between 580 and 630. So the green light has the smaller wavelengths of the two. If the wavelengths are small, that means the frequency of the photons has to be large, and if the frequency is large, the energy will be large. So which one of these two splitting patterns has a large splitting energy? It's the first one. So the first one is the one that must absorb the green light. It will therefore be seen as red. For the second one, just to verify, if it has a small splitting energy, it must be absorbing a small amount of energy, and a small amount of energy would give a photon of a small frequency, and a small frequency would have a large wavelength, and that would mean it would be absorbing the large wavelength of orange light, and so therefore it would produce a blue solution. Number 6. The tetrabromo cobaltate 2 absorbs electromagnetic radiation with a wavelength of 3.4 times 10 to the minus 6 meters. Determine the splitting energy of the complex ion. So if you know the energy that absorbs, that energy will be exactly equal to the splitting energy between the lower and higher set of d orbitals. So using Planck's constant, the speed of light, and the wavelength that's absorbed by the complex, we can calculate how much energy the photons have that cause the promotion of the electron, and therefore that equals the splitting energy, and this comes out 5.8 times 10 to the minus 20th joules. Number 7, identify the Lewis acid and the Lewis base in each of the following reactions. The first one is a reaction between a copper-2 ion and 4 ammonia molecules. The copper-2 ion has no electrons in its outer shell, but the ammonia has a nitrogen with a lone pair. That lone pair can be donated, and that's the definition of a Lewis base. The copper-2 ion can therefore accept that lone pair. That's going to be the Lewis acid. B, the reaction is between iron-3 ions and 6 water molecules. The iron-3 ion has no electrons in its outer shell, but the water molecule has a pair of lone pairs. One of those lone pairs can be donated to the iron, so the water will be acting as a base. The iron can accept the lone pair. That's going to be your Lewis acid. C, the reaction is between Bf3 and a fluoride ion. The Bf3 molecule has a central atom boron that does not have a complete outer shell. It can accept an electron pair, and the fluoride ion has 4 lone pairs. It can donate one of those. So if the fluoride ion can donate a lone pair, it's a Lewis base, and the boron atom can accept the lone pair. That's going to be the Lewis acid. Finally, for the reaction between sulfur trioxide and water to form sulfuric acid, when sulfuric acid gets formed, this is hydrogen sulfate, H2SO4, you're going to actually have a sulfur bonding to 4 oxygens, and then the 2 hydrogens will be bonded to 2 of the 4 O's. So what essentially has to happen here is that sulfur needs to make a bond to a 4th oxygen. So where's it going to get that from? It's going to come from the lone pair on the oxygen in water. That lone pair can be donated, and if that gets donated, the sulfur will accept it, so therefore the sulfur trioxide will be the Lewis acid.